This is a video to show solutions to the worksheet problems on the exponential and logarithmic functions derivative rules. Just at the top here, we're reminding ourselves that the basic rule, the chain rule involving exponential functions, is that when you take the derivative of e to any power, you get the e to that same power, and then times, by the chain rule, the derivative of whatever the power was. So a good example of that is the first problem here. We take the derivative of e to this polynomial, we get e to exactly the same power times the derivative of that power. And so usually it's easier to write when you're multiplying something times the power of e, it's usually easier to write it before the power. So this derivative is just 2x minus 2, but I'm going to write it over there in the front instead of at the end. So I'll say it's 2x minus 2 times e to the x squared minus 2x plus 3. And that's it. Number 2 doesn't use the chain rule, it uses the product rule. You can see that because it's got a times here, so something times something, and that's the main thing to identify. We don't really care what's times what, we just want to know that's the product rule. And so the product rule states that the derivative will be each of these things times the derivative of the other, and as we said, the derivative of the x. So this is the same as this. There's nothing to do. And the derivative of x squared is 2x. And so if we want to simplify that, generally what can happen with these e to the x is it's not unusual for an e to the x to be able to be factored out. So I could rewrite this as x squared plus 2x times e to the x. And it's not really necessary in terms of the derivative being correct, but as we discussed in class on Friday, if we're trying to find out where, for example, that's equal to 0, or whether it's positive or negative, then that form of it is much easier to use. Number 3 is quotient, so we write down what the quotient rule says to do. The quotient rule says to take the denominator times the derivative of the numerator minus the other way around. And divide by the denominator squared. So in the top here, see if I can fit it all in here. In the numerator, the derivative of e to the x plus 1 is just e to the x. The derivative of the x is e to the x, and the derivative of 1 is 0. So I'll have 3x plus 1 e to the x there. Oops, not plus, minus. And then here, the derivative of 3x plus 1 is just 3. So I have minus 3 times e to the x plus 1. And so that also can be simplified a little bit, but I don't have room here to do it, so I'll just leave it like that. The fourth one is, again, that's the chain rule. That's just e to a power. So just like in the first problem, this is like e to the box. So the derivative is e to the same thing times the derivative of the thing. So notice the similarities between that one and the first one that we did. We're just taking the exact same expression and times the derivative of the power. To do this, we would want to rewrite that x to the 1/2 and do our normal power rule with that. So if I do that, I'll have e to the square root of x, and then I'll have times 1/2 x to the minus 1/2. And again, that's simplified, but you can rewrite that with square roots and fractions instead of negative exponents, if you want to. Number 5, the derivative here, the 1,000 we just leave alone. Then we have the derivative of e to a power, and so that's exactly the same rule as in number 1 and number 4. So, well, I guess there are t's in here, not x's, but so just like in the other problems, it's the e to the same power times the derivative of the power, and the derivative of the power here is just 0.02. So, and so it does happen often that you'll have stuff, the chain rule always makes stuff multiply at the end, and if you have stuff that's already there at the beginning, you want to combine those. So, so I'll have the 1,000 times the 0.02, which is not a hard thing to do, times e to the 0.02t. So in the application problem at the bottom of the page, these are just not really word problems, just making sure we understand the difference between plugging in a number into a function versus plugging the number into the derivative and interpreting it correctly. So the first question just asks how many units we expect to sell if we set the price at 190. And so that's just a matter of paying attention to the problem. The 190 is X, that's dollars for price. And how many we expect to sell is the demand in thousands, so that's the Q. So basically this is saying what's Q when X is 190. And so it's just a matter of plugging in 190 for X into this to this relationship. So if you do that, you get approximately 73 point, looks like 0.6 or so, one decimal place. And the units here, these are thousands of tablets. So in other words, if we set the price at 190, according to this price demand function, if we set the price at $190, we expect to sell 73.6 thousand tablets. Marginal demand, as it says, is just Q prime of 190. So to do that, I first need to know what Q prime of X is. And I did not actually write down what 230. So the correct derivative here should be negative 1.38 e to the negative 0.006x. And that is using, that's just keeping this number still. So leave the 230 there and then take the derivative of this using the chain rule. It's very similar to the number 5 when we did up here. And so the negative 0.06 that's there was going to come out and be multiplied by the 230 the same way these two numbers get multiplied together. So that's where the negative 1.38 comes from. So just try it and see if you can compare to that final answer. Anyway, so then Q prime of 190 means put $190 in for X. And if you do that, you get approximately, let me change this to say approximately negative 0.44. And so the units on this, remember the output units are in thousands of units. So output is in thousands of tablets, output of Q. The input into Q is in dollars. And so the derivative is always rise over run, which means it's the output unit per input unit. So this is thousands of tablets per, the word per dollar. The inputs are in dollars. So in other words, if you are moving the price by $1, so increasing the price by $1 should change your demand by negative 0.44 thousand. So that's about 440 tablets. So in other words, your demand drops 440 tablets for every $1 that you raise the price when you're pricing things at the $190 mark, $90 mark. On the back page, we're using primarily the rules for the log function, and so our general chain rule for the log function is the derivative of the natural log of something is just 1 over that something times the derivative of that something, and that rule gets used right away in number 1. The derivative of this will be 1 over x squared plus 3, since that's the stuff that's inside the log, and then times the derivative of x squared plus 3. Which of course is just 2x. This is the derivative of x squared plus 3 is just 2x. We often see this written this way. So if you see a rational expression like this, it probably came from a logarithm, just because 1 times 2x is 2x. And so it's just a simpler way of writing the answer. The second problem here is the product rule, and so I'll just write down what the product rule says to do. And then the derivative of x squared is 2x, of course, and the derivative of log x is 1 over x. And so we have plus log x times 2x. And so this latter thing doesn't simplify at all. You can't really do much with non-log stuff combined with log stuff. But this simplifies to be x, so that's not, so something can be done there to make that a little bit easier. So we don't have fractions in there, but we still have the log. In number 3, we know that, actually let me start up here. We know that our quotient rule tells us that we're going to have the denominator times the derivative of the numerator minus the other way around. And again, the derivative of log x is 1 over x. So this guy is 1 over x, and this is just 6x. And there's really not going to be a whole lot you can simplify with this. So 3x squared plus 1 times 1 over x minus log x times 6x. And that's all divided by 3x squared plus 1 squared. Because you have this distribution, this 3x squared plus 1 times 1 over x, that doesn't really, I mean, you can multiply that through, but you can't get rid of the fraction there. Number 4 is just like number 1. The derivative is 1 over this thing that's inside the log times the derivative of that thing. And so to do this, I need to write that as x to the 1/2 power, and then the derivative will be 1/2 x to the minus 1/2 power. But if I rewrite that back in terms of square roots, something kind of nice happens with simplification here. The derivative of square root of x is equivalent to 1 over 2 square root of x if we take it back away from 1/2 x to the minus 1/2. And if you do that, then the square root of x times the square root of x. The square root of x times the square root of x is just x, so this ends up being 1 over 2x. So that does simplify quite a bit if you want to. And then number 5 is just like number 3. It's a quotient rule problem, and I just threw the e to the x in there to remind us that we really can deal with any combination of these things when they're together. So again, I'll write down what the quotient rule says to do, and then actually do it. The derivative of 1 plus log x is just 1 over x, and the derivative of e to the x is just e to the x. So if you think about it, each of those two terms in the numerator still have an e to the x in them, so I could factor that out, and I'll just go ahead and do that. So the first term here would be e to the x times 1 over x, and then this is e to the x times that stuff. So I could just say minus 1 minus log x. And the only reason for doing that is that I noticed that because there's an e to the x that factors out of the top, the denominator here is just e to the x times e to the x. So you could just sort of cancel one of those with one of those if you wanted to, but you could just leave it like it was. In the application problem, it's just like the one on the previous page. So the first question is really just asking what is P of 50, and we can do that by just matching up. It says 50 ads, and we look up here and say, oh, well, that's what x means. And what percent of the target audience? Well, that's what P of x means. So if we just match words, we realize that they're asking us here, what is P of 50? And so that's just a matter of plugging in to the formula, and I get 75.2. And the units here, this is percent of the target audience. So in other words, when I've run 50 ads, I will have achieved 75% of my target audience buying my product, my game. The second question is about the derivative. So I first have to find the p prime of x formula, and this looks like a quotient, so you could use the quotient rule, and that's fine. Don't forget in the quotient rule that the derivative of 100 is 0. That's part of the quotient rule. But if you do the quotient rule correctly, you will have you'll actually have 490 e to the, sorry, I'm copying it down from my paper, 1 by x over 1 plus 49 e to the minus 0.1 x squared. So if you do the quotient rule and simplify it, again, remember the derivative of 100 is 0, that's what you'll get. And then so p prime of 50 is approximately 1.87. And the units here, again, we already identified the input and output units. The input units are in ads, and the output units are percentage of target audience. So this is in percentage of audience per, the word per, additional ad. So in other words, you're at the 75% mark now. For every additional ad you run, you expect that 75% to go up by 1.87 percentage points.